Hello and welcome to Diplomatic Derivatives. In today's video, we're going to explain whether a given set is a group or not. So in the previous lectures, we tackled what a group is and what are the four axioms that need to be proven for something to be qualified as a group. In today's video, we'll be applying those axioms on the group Z+ and see whether under addition it's a group or not. We're going to see what is Z+. Z+ is the set that represents all positive integers. So it's C+ is equal to 1, 2, 3, 4 and so on. As we talked about in the previous video, that we do not need to confuse it with the operation. So Z+ and the operation is addition. The statement itself, the statement of this video is Z+ under addition is not a group. So that in a notation we can write Z+ the set and this is the operation. So this plus over here is not the operation. This plus represents the set itself, which is a set of only positive integers. So you exclude all the negative integers and you exclude 0 as well, because 0 is neither positive nor negative, and you write only the positive integers, that is 1, 2, 3, 4 and so on. So that's the set, and the operation on the set is addition. Okay, and we have to prove whether this is a group or not. So first of all, the statement why it is not a group, because the absence of identity element. Now we'll see why are we saying that there is no identity element in the group, in the set. Okay, first of all, as a group, for something to be called a group under some operation, for example is addition, a set must satisfy these properties, the four axioms. Now what are those axioms? Just to revise: closure, that is adding two elements of the set gives another element in the same set. Okay, so for example, if we have 2 and 3, 2 plus 3 is equal to 5, and that 5 has to be in the set itself. So if that's true, the first property is agreed on. Okay? Next we have monoid. Now monoid is a different term, we didn't talk about it in the previous video. Monoid is some set which can be called a monoid if these two properties are fulfilled. So we have associativity, that is a plus b plus c is equal to a plus b plus c, and identity element exists, that is there is an element e such that a plus e is equal to a for every a. So for any set, if there is associativity is true, identity element exists, right? So we have associativity and we have the identity element. If these properties are true, then that set will be called a monoid. Okay, and the fourth property, so we have the first group axiom, we have the second group axiom, third group axiom, and now the fourth one, which is inverse. So inverse must exist. For every element a, there is another element a inverse such that a into a inverse gives us the identity element e. Okay, so if these four properties are fulfilled, we can testify that a given set is a group. What is the problem with Z now? Z+, that is set of all positive integers, it's closed under addition. So the first property, it has to be closed under the operation. Operation is addition, so taking two elements, 2 plus 3 is equal to 5. 5 is element of Z+, therefore it's true. Associativity, addition is always associative. Okay, so whenever you perform the operation of addition, it's always going to be associative on any set. Okay, but there is no identity element in C, because we know that the identity element for addition is 0. Now if we take the elements, any element from Z, for example, we're taking 3. 3 plus 0 is equal to 3. We get the same element, right? But in this case, when we're talking about Z+, we'll just write the set over here. Set Z+ is what? It's 1, 2, 3, and so on, right? That's the set. So we do not have 0 here, because 0 is neither positive nor negative. We do not have 0 in the set. 0 is the identity element for addition, right? For the operation of addition, 0 is the identity element. It's not in the set, therefore identity element does not exist. Okay, so we say that a plus 0 is equal to a for any a. It's not a part of the set, so Z+ is not qualifying the third group axiom, that is the presence of the identity element. Since identity element does not exist, it fails to be a group. All right, so this is the problem with Z, why Z+ under addition is not a group. This is the proof of this theorem. Okay, now what what we're going to do is we're going to change the operation from addition. We are going towards multiplication. So we have the same set z plus, which is 1, 2, 3, 4, and so on. And we are going to change the operation from addition to multiplication. Okay, first axiom under multiplication, it has to be closed. It's closed under multiplication. 2 into 3 is equal to 6. 6 is a positive integer. It's part of the set. Okay, it's also associative. We get 2 into 3 into 4 is equal to 2 into 3 into 4, which is 24, and it's true. Again, 24 is part of the set. Also, the identity element exists. So when we talked about addition, the identity element did not exist in the set C+. But in set C+, under multiplication, the identity element exists because the identity element of multiplication is 1. So you take any element from Z and you multiply it with 1, so you get the element itself, right? Therefore, that element is the identity element. That is 1 is the identity element, which gives you the same element. 2 into 1 is equal to 2. So you get the same element. But inverse does not exist. Now, fourth axiom is not true for the set C+ under multiplication. Why? Because A inverse is not included in C+. We have, for example, we take 2. What is the inverse of 2? It's 1 by 2, right? Now 1 by 2 is not part of the set because the set of integers is only 1, 2, 3, 4, and so on. Only positive integers, right? 1 by 2 is not part of the set of positive integers. Inverse of all these elements are not part of the set. Therefore, the inverse does not exist. Okay, since A inverse isn't included, the Z+ under multiplication fails to be a group. Reason? Due to the absence of the inverse. Okay, so just to revise, Z+ under addition is not a group because of the absence of addition, because of the absence of the identity element, and Z+ under multiplication is also not a group because of the absence of the inverse. Okay, so these are the two proofs. That's all for this video. So in this video we tackled the set, any set for, so basically the means of this video was to make you understand that whenever any set is given to us, this is how we are going to apply the 4 rules, and that's how we'll prove whether that set is a group or not. If any one of the axiom fails, therefore the set is not a group under that operation. Okay, if you like the video, please like, share, and subscribe. And in the next video, we're going to talk about involution. Now, what is an involution? And we're also going to tackle a theorem related to involution. So if you like the video, kindly subscribe to my channel and follow for more exciting content related to mathematics. And that's all for today. See you in the next one. Bye bye.